Imagine a brand new skyscraper, a beacon of modern engineering. Now, picture massive cracks, spiderwebbing across its foundation, a multi-million-dollar repair bill, and a forensic investigation that points to one single, flawed assumption made in the design software. This isn't a hypothetical, it's a reality that has cost firms their reputation and clients their fortunes. In our last video, we concluded that even the most advanced AI or digital twin will fail if the underlying physics are flawed. Today, we expose the most common and dangerous flaw in foundation modeling, the myth of perfect soil structure interaction. Welcome to Strong Foundation Engineering. Let's dig in and understand why the way we model mat foundations is often fundamentally wrong. Almost every structural analysis software asks for one simple input for mat foundations: the modulus of subgrade reaction. It feels so easy, a single number to represent the entire soil mass. But here's the trap. The subgrade reaction is not a fundamental soil property like density or friction angle. It's a mathematical convenience, a mirage. Think of it like this. Asking for the subgrade reaction of soil is like asking for the bounciness of a trampoline. Is the trampoline bouncy? Well, it depends. It depends on the size of the person jumping, where they land, and how stiff the trampoline mat is. Similarly, the value of subgrade reaction for the exact same soil changes depending on the size, shape, and stiffness of your foundation. Plugging in a textbook value for subgrade reaction is one of the most common yet critical errors in foundation design. It assumes the soil's response is independent of the structure it's supporting, which is never true. So, how do engineers simplify this complex reality? Historically, we've used two extreme assumptions. First, the rigid model. This assumes the mat foundation is infinitely stiff, like a thick concrete plate. Under load it settles, but it remains perfectly flat, forcing a uniform settlement. The soil pressure underneath, however, becomes non-uniform, higher at the edges. The second is the flexible model. This assumes the mat has no stiffness at all, like a rubber sheet. It bends perfectly to match the soil pressure, which means under a uniform building load, the settlement is non-uniform, dishing in the middle. The truth? Every real mat foundation is semi-rigid. It's a constant negotiation. The mat tries to stay flat, and the soil tries to deform. The final shape and the resulting stresses are a compromise between the structure's stiffness and the soil's resistance. This brings us to the core of the problem in our software, the Winkler foundation model. This is the bed of springs model that underpins the calculation of subgrade reaction. It simplifies the soil into a series of independent, disconnected springs. If you press down on one spot of a Winkler foundation, only the single spring directly underneath compresses. Your software sees no connection to the spring next to it. But we all know that's not how soil works. Soil is a continuum. Pushing down on one point creates a settlement basin that influences the area around it. It's the difference between a mattress made of independent pocket coils versus a waterbed. On the pocket coil mattress, you can push one spot down without affecting the rest. On the waterbed, pushing down anywhere creates a depression that pulls the entire surface with it. Most structural software treats our soil like a cheap mattress, not the fluid-like continuum it truly is. So, what's the alternative to this flawed spring model? It's the continuum approach. Instead of trying to represent the soil with a single artificial number like the subgrade reaction, we model the soil for what it is, a three-dimensional solid volume. Using advanced tools like 3D finite element or boundary element methods, we define the soil using its true fundamental engineering properties, the elastic modulus and Poisson's ratio. This is a complete paradigm shift. We're no longer asking the software to guess the soil's reaction based on a flimsy spring analogy. We are showing the software the soil itself and letting the laws of physics calculate the interaction directly. It's the difference between describing a car by its horsepower alone versus giving an engineer the full CAD model of the engine. This isn't just an academic debate. The choice between a spring model and a continuum model fundamentally changes the calculated behavior of the foundation. In a continuum model, even under a perfectly uniform load from the building columns, the mat will settle more in the center and less at the edges. Why? Because the soil in the center is confined by the soil all around it, allowing it to compress more, while the soil at the edges is freer to bulge outwards. The spring model is completely blind to this. It cannot capture this coupling effect. As a result, the Winkler model will predict a completely different settlement profile, and more importantly, a completely different pattern of bending moments, which are the forces that your steel reinforcement must resist. And that brings us to the steel. The entire purpose of these complex models is to figure out where to put the reinforcement. The bending moments tell you where the concrete is in tension, and where you need rebar to prevent it from cracking. If your model incorrectly predicts the moments, your reinforcement design will be wrong. A Winkler model might tell you to spread your steel evenly, while a Continuum model will scream at you to concentrate heavy reinforcement in the center of the mat to counteract that dishing effect. Getting this wrong means you are placing expensive steel where it isn't needed, and worse, leaving the most critical tension zones completely unprotected. It's not an over-design or under-design. It's a misdesign. These aren't just academic debates. Engineers have bet millions, even billions on these modeling assumptions, and some have lost spectacularly. The choice between rigid, flexible, or a full continuum analysis is one of the most consequential decisions in structural and geotechnical engineering. It dictates safety, cost, and the long-term performance of our largest structures. But this leads to an even tougher question. For these advanced continuum models to work, they need good data. An AI or a finite element model is only as good as the soil parameters, elastic modulus, and Poisson's ratio that we feed into it. In a world of tight budgets and limited site investigation, how do we get the reliable data needed to make these models worthwhile? That data gap is the next great frontier. So here's the billion-dollar question we'll tackle next time. What happens when a team of world-class engineers, using the best software available, models a massive mat foundation as perfectly rigid for a structure that was, in reality, extremely flexible? The answer led to a catastrophic failure that fundamentally changed how we design these foundations forever. In our next video, we will perform a full forensic analysis of that very case study. You don't want to miss it. Subscribe and hit the notification bell to be the first to know when it drops.